Just want to thank Jeremy for the invitation. So I'm just by no means an expert in this. So I just want to share some of my perspectives and the things that I've applied and then my thoughts. And if there's anything that's not clear or you disagree with, I'm happy to discuss. Again, this is only going to be my perspective. And then some of the quote-by-quote advice I'm going to give you guys will be also based on my personal experience. So without further ado, in this lecture, I'm going to talk about estimating these dynamic distributed choice models. And just before I even start, so just the whole agenda is basically to give you a sense of how these models are estimated and what are the tools that you can use to estimate it, what are the practical concerns. And I will first introduce some theories on estimating these models. Basically, we'll be just recapping what Jeremy has talked about. And then we'll talk about estimation. And I tried some version of this lecture at Wharton to the PhD students. I get some feedback. So the very first thing they asked me was like, why are you doing this? And then so that's sort of similar question I would get when I present structural work. So it may not come in the form as why are you doing this? They will come in the form that why you're making these assumptions and these assumptions don't match the data. So these will be the type of questions you will get when you come up with your research question, write a paper, and it will be the same question you have to ask yourself when you make trade-offs in building models, right, and putting the model into estimation. So in terms of the benefits, I'm pretty sure Yufei had talked a lot about the benefits of structural modeling, and I fully agree with what she was talking about. I checked her slides, and there's nothing that's inconsistent with what she said. So basically the benefits, so this is just to recapping what she said, is including allowing for estimating unobservable constructs. For instance, like earnings management. What is the percentage of firms that are managing earnings in the economy? So that's obviously an important question to ask. So structural estimation allows you to do it. The second one is basically to conduct policy experiments. So there's some state of the world that we don't observe, and especially you want to study some policy interventions. For instance, in my paper, I look at, with Edwidge, we look at mandatory audit firm rotation in the US. So that's not allowed. So that's basically a state of the world that you don't observe, right? So we use a structural model to conduct this policy experiment. And in the second half of the lecture, I will just basically present that paper, and you guys can give me some feedback, think about how to make the model better and what are the possible extensions you can run on this model. So that will be sort of an example of this. The third one, I will call it, it's very similar to the first one. I call it dealing with missing data problems. Because sometimes you're interested in something, but you don't have data. Maybe the data is really hard to be obtained. Or maybe you just is a theoretical construct that you don't just observe in the data. So in that case, you may want to impose some assumptions that are commonly accepted, and then assume that you observe the data. So the data will be generated by, let's say, simulation. To give you an example, like in marketing literature, so people are interested in the effect of consumer learning. So consumers learn over time the quality of the product, but you don't directly observe how they learn. Instead, you build a structural model of consumer learning, and then you integrate out the component that you don't know. So that's how they do it. And finally, you can explicitly account for the economic interactions among agents. For instance, in a contracting setting, then you can model that interaction explicitly. You can even make it more complex. You can estimate dynamics or even dynamic games. So that would allow you to answer more interesting questions than you otherwise will be able to answer using reduced form regressions. So in reduced form regressions, you can't really model dynamic interaction among agents. You can only come up with an equilibrium and then test the implications of that equilibrium, right? So those are the benefits. Let me just put, yeah. Yeah.
That sounds like we're talking about the benefit is you can use a model to estimate something you can't see. But then there's another point you're making about like being able to average out something and more. Can you elaborate this a little bit later in the slide?
Yeah. So these the consumer learning example, right? So the way that they model it is that assume that consumers observe, they have some prior beliefs about the quality of, say, detergent. And then that prior belief is not something that econometrician observes. So you're going to assume, let's say, it's distributed normally. And then that will behave like an error term. In the end, you have to integrate it out in the moment condition. So that's what I mean. Let me just first figure this one out, and then I'll continue. All right. So this is a benefit. So the common critiques, and this is something that you've also covered. So the imposed structure is subjective. So this is completely unavoidable because you always need to start with some model, right? So you have to justify why you're starting with the model. So there are always going to be someone who don't like the model, so that's fine. As long as it captures the key economic question that you're interested in. So I think that would be a good starting point. We are also unable to model all the related forces that could drive the outcomes. And as Yufei also talked about, it's not, if you have a more complex model, it doesn't really mean that it's a better model, right? So you always need to make the trade-off, and there will always people who ask, why don't you add this, why don't you add that? So you need to ask yourself whether those forces are the first order forces you're interested in. Some common fallacies. So I think they are fallacies, maybe they're not. So this, again, is my personal perspective. So the first one, the people will say, okay, so you must be estimating something that's completely junk because your model is not realistic. And for instance, I may start with the paper by saying that Earth is the center of the universe. Okay? So that will be a wrong answer because people will say, obviously, Earth is not the center of the universe. So whatever you're estimating must be off. But still, even in this case, let's think about this. So is it really problematic if I'm just studying the movement of the moon around the Earth? So if the moon is the objective that you're studying, then assuming the Earth is the center of the universe will give you a pretty good first-order approximation. Of course, the existence of the sun is going to tweak the movement of the moon a little bit, but as a first-order approximation, it's not that far away. So my point here is that to some extent it's a writing issue. Because if I imagine I start with the paper by saying that Earth is the center of the universe, so that's going to stick to your mind from the beginning, and you are going to be very uncomfortable with it. Another thing is that you need to justify why you're making some key assumptions that deviates from the prior literature. So that's my view. Of course, that doesn't mean that it's okay to make wrong assumptions. It's just you need to make sure that it's not really driving the effect that you're interested in. All right. Again, the fact that a model omits some non-empirical facts, I should say be carefully here, does not necessarily make it inappropriate. In a lot of cases, it would make it inappropriate, but it doesn't necessarily make it inappropriate. All right. The second fallacy is that structural models are identified only based on functional form assumptions. Exclusion restriction actually can be incorporated into structural estimation. So you can identify based on the usual exclusion restrictions, like you have an instrument. Other econometric issues like selection biases, survivorship biases, controls, and standard errors can also be accommodated. So the reason why I'm bringing this up is that there is a paper by Welch that's in Critical Finance Review. So he basically summarized the common problems with structural modeling. And these are one of the issues, because one of the critiques is that the existing structural models don't really deal with the selection biases, survivorship biases, and standard errors. So that's, they can be dealt with, right? So Jeremy has talked about using bootstrapping. So there are various tools. All right. So the next part of the lecture, so I'll just briefly talk about value function iteration and the policy function iteration, and then I'll apply the technique to one of my papers with Edwidge, and then we can discuss there. I understand that this is pretty much lecture based, and then I'm just talking about the tools that you're going to use. But the objective I'm going to have is that make sure that you understand exactly how it's applied. And in the afternoon, I'm going to ask you guys to code stuff up, so to get your hands dirty. Because until you do, so everything will sort of make sense. At least that's what I felt when I first take structural class. Everything will kind of make sense, but you're kind of sitting outside of the window looking into a room. I think it has, if I don't have enough time to cover all the materials, I'll cut some of them and actually work on the problem I post online. So it will be a simple auditor switching problem, and I program it using R, so you can use MATLAB, that'll be fine as well. But just to get some sense of how things are applied. Yes?
All right, so imagine you're like a field experimentalist,
Yeah.
build out structural. So how do I deal with the issue that you would get from editor, which is to show, or how do I evaluate a paper to know whether or not the assumptions that you're making are indeed like something that was an example, like the Earth example, as opposed to what the common criticism is, it's just something you can use to solve it. So we do p-hacking in empirical studies, right? We
Yeah.
always talk about ex post justifying the assumptions to get the result. Right here, your ex post is justifying the assumptions so that you can solve it.
Yeah.
Right? How do I get around, or how do I evaluate whether or not that assumption is reasonable versus?
That's a great question. So, in the previous conference at Stanford I attended, so there was this discussion about, whether assumption makes sense or not. Really, it depends on, I would say there's no right criteria to evaluate whether assumption makes sense or not. So it's up to the authors to justify why they're making the assumptions.
Are there assumptions that are being made in these that, like, if I was a reader, I should be more or less, like, sort of worried about just because they are just something that makes it so that it's tractable?
Yeah.
Just because it's tractable doesn't make it better.
Right, it doesn't make it better. So I understand that. So to give you an example, let's say that a lot of voluntary disclosure models assume that management discloses the truth. Then you can come back and say that we know lots of examples in which management does not disclose the truth, and then wouldn't that affect your estimation? So here's going to be my answer to that question. So there is a paper I think it's review paper of management forecast, at least in that setting. So what that paper shows is that at least management forecast is not that far away from realized earnings. So if there is any earnings management, then it's managing the realized earnings, not the forecast. So in other words, they are maybe managed together so that on average, management forecast is centered around the realized earnings. So that's not far off. So then you can say, okay, so there will be earnings management. So you're making an assumption that's wrong, but then at least in the data on average, it seems to be right. So that's the right way. But that's a costly way because some of the assumptions are not really observable and testable. So in that case, it may matter, right? So then I would say I can try robustness checks. So you see one example, like, in my paper with Edwidge, so there will be some of this that's going on, so we're going to try different policy experiments. All right. Okay, so let's just set things up. So remember, we're talking about dynamic discrete choice problems, so everything will be discrete. The choice will be discrete. You can think about whether the firms disclose or not, so 0, 1. You can think about firms choosing like capital stock levels, so like, in discrete chunks. So these are discrete choice problems. So to set it up, let's say time infinite horizon problem, time from 1 to infinity. This can be generalized to finite horizon problems, but typically we deal with infinite horizon problems. State space is S. So state can include variables that either observable or unobservable. In other words, the error terms. So unobserved ones will be the error terms, and observed one will be the regressors. So you can think of it that way. Then a set of actions based on the state. So agents observe the state, and they choose certain actions. Okay, so that's the simple setup. In many applications, the set of actions does not depend on the state. So let's say disclosure problems. So if a firm either disclose or not disclose, so irrespective of the performance, they have the two options to choose from, right? So they can choose to disclose the performance or not to disclose it. But for some accounting problems, the set of actions may depend on the state space. For instance, your dividend policy may depend on whether your covenants are violated or not. Right? Maybe there is a term in the covenant that says that you cannot really issue dividends if you violate the covenant, right? So for some problem, the action may depend on the state, but we're going to deal with a simple problem where the action does not depend on the state. Okay, that does not depend on the state space. Of course, the actual action that you're going to choose will depend on which state you're in, but then it's not going to limit the set of actions that you can choose from. So that's what I mean. All right, so decision process is assumed to be Markov. A decision maker will choose an action AT from the set of actions in period t, given the current state of the world, st, and receives utility of u of st and at. So at will be the action. So that's the problem we are dealing with. The state evolves according to a probabilistic distribution named P, given the current state. So this is a Markov problem because it depends only on the current state. All right? So it does not depend on history of states, and this is just for tractability reasons. So this goes back to Eric's point, whether that's reasonable or not. So you can always find cases in which this is not reasonable, but this is what we focus on. So this is purely for tractability reasons.
But intuitively, the third state would be a consequence of the previous state.
Right, so that's definitely allowed. So it will be a consequence of the previous state, but then your decision will be, let's say I give you the previous state, I give you the current state. The assumption is that I'm going to make my actions just based on the current state. So to some extent, it's not a bad assumption because that's the most relevant one. So you're going to put most weight on the current state. So that's what this is assuming. Yeah.
Super quick follow-up. Now, when you do these models, is it hard to run robustness tests where you do a simulation where you throw that assumption out and see if it holds?
I think if you can if you assume that it's just depend on the current state and the previous state, so that's easy. It's just if you don't impose any structure, that will be hard.
But so imagine you did this and you get a result, and then you redid it, and you just added the previous state, and you find a different result. Right? What do you do at that point? You keep going and say, okay, I'm just going to assume it's Markov and I'm good, or do you shoot?
So I would just go back and think about the model, like whether why that was the case. Why would the data tell you that it depends on the history of the actions, and I would adjust it. Because if you go back to the very first period, then there's no identification, right? So because you just have a cross section, you don't have time series.
I'm only asking these questions to people in the room too. I know the editors of the journals, right? So you
Yeah.
have one theory editor among the two top that's a very purist, right? So in a sense, all I'm asking is how to think about justifying it in a way that people can, never mind.
Yeah. So I think this kind of Markov process is pretty commonly accepted. I would say I don't, when I present this paper, I've never seen that people challenge this assumption. And as I said, to some extent, it's a pretty good first order approximation to a lot of things. Like if you see people studying the persistence of guidance, the guidance decisions, they typically just look at the previous year or previous quarter guidance. So I don't see that it's a huge problem. But the more problem comes from the model structure, the period utility function, what you're assuming. That's my take. Okay, so decision rule is just a mapping of from the current state to a feasible action, and the policy or strategies just mean that the set of decision rules from the time zero to the infinity. Okay, so I just basically set up just to remind you guys. So there's a current state. The state can change over time, and you're just making a decision given the current state. Okay. So I haven't really talked about what is the maximization problem. Here is the maximization problem. So the maximization problem is that you are going to maximize the expected future utility, discounted future utility, and the expected total discounted future utility for a given policy. So the policy is the decision rule, right? So the action that you choose in each state of the world. So given the decision rule, given the policy pi, then the expected utility is discounted future utility. The optimal policy is among all the possible policies the best one that gives you the highest utility. So the maximization problem right now seems pretty daunting because you don't know the policy space. So there could be infinite amount of policy that you can choose from. So that's where the Bellman equation comes handy. So we can write the problem into two pieces that Jeremy just talked about. The first piece is the current period utility. So that's from choosing, given the current state. Okay, so given the current state, choosing an action like disclose or not disclose. The current state you can think about as from performance. Okay, given current state from performance, you choose to disclose or not disclose. That's going to give you some utility at the current time. But your disclosure choice may also affect your future utility. So that's the second piece. So that's the integral because the future is random. So that's the expected value of the value function, okay, given the future, the evolution of the future states, given the current state. So that's the second piece. That's the value function piece. And then more formally, we can define a contraction mapping based on this. So current period utility plus the discount factor of times the expected future utility. And the solution to this Bellman equation would be a fixed point. Okay? And I'll give you a theorem here. So if V is the solution to the Bellman equation, then we get the value function. Furthermore, under the model assumption stated above, basically the discrete choice problem that we are facing, and in addition that the utility function is bounded. So in this discrete choice problem, you can always guarantee that there is a unique solution to the Bellman equation. So that gives us the value function. So in other words, if you work with dynamic discrete choice problems, you are assuming discrete state space, discrete choices. In addition, your utility function is bounded, then you're guaranteed a solution to the dynamic discrete choice problem, so a unique value function. This is really important because it guarantees that you start at random place when you try to solve the value function. It iterates until it converges. It wouldn't give you. It will converge to a unique point. So that's really important. Otherwise, it will just bounce around, and you're going to, not be able to get anything out of the value function iteration. Okay. So I'm going through this really fast because Jeremy has talked about it, so I don't want to repeat too much. But I think it's kind of, it makes sense to set it up so that, because for those of you who just heard of value function iteration for the first time, it may take some time to digest. Okay?
Can the Bellman equation be solved analytically without using any software?
So in rare cases, like one of Jeremy's problems, the problem that we just talked about, you can solve it. But in most cases, if you want to make the model even like a little bit more realistic, then no, typically it's not solvable analytically. But if you can do it, that would be great, right? So then it'll be much faster. So you have just an equation. So you always want to try it. Yeah.
When would you use the Bellman equation versus, I don't know much about this, but like optimal control theory, so using like the Hamiltonian or other.
Oh, so so it's the same. It's really the same thing. So you're talking about Ivan's lecture, right? So the optimal control problem in continuous time. So that can be really hard to understand. So it's basically the same thing with the stochastic component. So there's a Brownian motion. So instead of the probabilistic distribution here, so that's really simple. So here, the probabilistic distribution, if you replace it with Brownian motion, then you have exactly the same. Of course, then if it's this optimal control problem, you have to think about the stop time. So that's all, which is also random. So it just gives you a really nice framework to solve. Yeah. But in theory, it's the same. Okay. So just I'm just moving really fast here. Okay. So there's two ways to solve for a value function. The first one, as Jeremy talked about, is value function iteration. The second one is called policy function iteration. So before I even go into the details, let me just clarify one more time, which Jeremy has already done, that at this point, we're not really estimating anything. So when I say we solve for a value function, this is assuming that we know the parameters that enter the utility function. So in other words, the functional form of u of s and a is assumed to be known at this point. Okay, so given this u, then what is the v star? So that's what we're trying to compute here. And that's why people say that structural modeling takes a lot of time because, you know, the outer loop really, so you're trying to maximize the likelihood function or minimize the moment restrictions. And within it, every time you choose a parameter, then you have to solve for the value function. Okay? So for a typical Bayesian estimation, let's say if you use Bayesian estimation, you need 20,000 iterations at the outer loop. And then inner loop, you need to solve for value functions, right? And let's say your value function takes 1 second to solve. And then with multiply by 20,000 iterations, you probably would spend like around 90 days for you to get the outcome. So that's just too late. So you know that's why you need to be really careful with applying these techniques, and you want to make sure that your codes are super efficient. So 1 second to solve for value function is just too short, too long. You want to make it more efficient. Okay, but this is only Bayesian estimation. So if you use other techniques, then it could be faster. Okay, for instance, GMM. Okay. Briefly, value function iteration, we already talked about this. So I just briefly summarize it on one slide. So you start with some arbitrary value. Of course, here, when I say arbitrary, just in theory, empirically, you want to pick a smart point because that will save you time. So it can save you like from maybe 30 seconds, so that makes a lot of difference. In the code example I'll give you guys in the afternoon, you can play around with it. You can see like how fast or slow it converges. Because this is one issue. Another issue like I will cover towards the end of the class if I have time will be you can use some functional approximation techniques. So these are super exciting because there are techniques that can make your code much faster. And these techniques, basically the technique that I know of, often depend on how you discretize the state space. Okay, so your state space, let's say firm performance, you know that it's continuous. And you just, to solve for the value function, you just discretize it into certain grid points, and then you connect the grid points. Right, so that's the idea. So why are we doing this? Because we don't have infinite amount of computing power, we don't have infinite amount of time, so you have to discretize. And these functional approximation techniques often are choosing which points, okay, which grid point you need to choose to have the best efficiency in approximating the value function. Okay, so that's different techniques we can use. I'll cover it in the end. So the general idea again is that you pick some random value. Okay, when you pick the random value, then the value function will be known. Okay, in other words, if you look at the equation on the right-hand side, the v of n, so I have a superscript n, so that means the value function from the nth iteration. So this is known, and then you can just compute everything here on the right-hand side and take the maximum, and that will give you the value function at iteration n plus 1. So this is how it's iterated. And you can, if you are used to programming in MATLAB, you can think about the v of n as a vector. So each vector will correspond to the state space. Let's say firm performance, high, medium, low. Then the value function would take 3 values. Okay, value function when performance high, medium, and low. And that's plugged into the right-hand side. You solve for the maximization problem. Then you get the left-hand side. So here, solving for the maximization problem doesn't even need first-order conditions because you have 3 points. You just performance high, medium, or low. So for each given point, you can compare like whether you disclose or not disclose and pick the optimal action here. Okay, so this doesn't need to solve for first-order conditions to get the maximum because you have a computer. Then you iterate until it converges, so that gives you the, in the end, the optimal policy. Okay, so that's sort of the idea. And in the afternoon, we're going to try to apply this. So if you have any questions about the steps, just you can ask me. So there's no reason to hesitate because sometimes I feel like when I sit down there and it's really hard to ask questions because I don't know like what I may have missed and I don't know whether that question makes sense or not. So just don't worry about me. So I'm not a super senior faculty who's going to judge you. So, so I learn from you guys as much as you learn from me. So it's really a bilateral process. So just feel free to ask me anything. All right. Okay. So the benefit of value function iteration is that it's a super robust method. Convergence. The problem is that convergence can be really slow compared to policy function iteration in many cases. But it's really less prone to coding errors, which you will see in a minute. In addition to value function iteration and policy function iteration that I will talk about, there's also modified policy function iteration, and there are various versions that you can even come up with by yourself when you apply the codes. But the value function iteration is something that you want to check in the end because it's, again, less prone to coding errors. And the convergence is much faster when beta is small. And why am I mentioning this? Is that when you code things up, you don't want to wait for too long a time. So you want to pick a beta discount factor that's really small and then check whether your codes are correct or not, because it will give you results faster. Okay, and then you can just pick the wrong level of beta. Okay, discount factor. Just in case you guys don't know, so discount factor in the dynamic discrete choice settings is it's impossible to identify. So you always assume some discount factors. Okay, so maybe from CAPEX models or from the best practice that people have used. Like in marketing guys, they often use 0.99, for instance. Okay, and there are papers that use experiment data to identify the discount factor. That you can use that too. Okay, question over there.
I just want to clarify, when you say this is a robust method, is it the robustness is coming because the initial choice of the value function doesn't matter, or is it some other thing, or have I completely missed the point?
Oh, so yeah. So what I mean by robust method is that it would always give you the right thing, but there are like say modified policy function iterations. Sometimes it will give you the wrong solution, but what I mean here, like for the problem we're dealing with today, is just the coding errors. You'll see in a minute what I mean by this. Okay. The second one is policy function iteration. So here, to code this up is more complex. Okay. So now we just choose random decision rules. Okay. So the random decision rules meaning that, let's say, when performance is high, I'm going to disclose. When performance in the middle, I'm now disclosing. When performance is low, I am disclosing again. So I just arbitrarily choose some starting point. Okay, assuming that's the optimal policy. So with the optimal policy, what I'm going to do is that in the second step, okay, I'll plug in the optimal policy into the per period utility function. Right, so my current period utility function will depend on the policy, the disclosure decision I choose, and then it would also depend on some other state variables, like say the number of analysts following, for instance. Okay, so that's the second step. The first be the U of S and D. So I already know the optimal policy. The question is, what is the V of N? So we still need to know the value function. And again, I'm assuming here that value function is unknown at this point. But if you look at the equation, the left-hand side and right-hand side had the same thing. Because, right, so the right-hand side is just a value function times a Markov transition matrix. The Markov transition matrix meaning is it's just capturing the evolution of the states. If the current state is high, what is the likelihood of the future state? Right? Is high as well or low? So it's just multiplying this by a Markov transition matrix. So then you can look at this, you move the beta times the transition matrix to the left, you can solve for the value function. Okay? So you just, from this equation, so you think about the V of N as like a vector on the left-hand side, and then the right-hand side is also a vector, so it's just a linear system of equations, right? So they can solve for the value function given the optimal policy. The problem with this, okay, the reason why this may get you the wrong solution is that you may get stuck here because the Markov translation matrix is really sparse. And then if you try, you see like if you try to solve the equation, then you need to invert the matrix. And we know that if the matrix is kind of sometimes sparse, it's not, has an yield property, then it will give you a problem. Okay, so that's the problem. And sometimes a partial value function iteration can be used if the matrix inversion is computationally difficult. So basically, instead of doing the policy function, so instead of solving this analytically, you can iterate the value function a few steps. And by a few steps, I mean that maybe 20 steps. This arbitrary number that you choose based on your experience and based on the data set. So the point here is that solving step 2, you can analytically solve it, but if it's not feasible, you can numerically solve it, okay, just by applying the value function iteration in the second step. And in the third step, then you update the decision rule. Okay, in the second step, we already compute the value function, that v of n is known. Then you just plug the v of n that you saw from the second step, and then you get the updated decision rule. Okay, so that's the policy function iteration. The reason why it's called the policy function iteration is that you choose a policy given the state, and then given the policy, you solve for the value function, and then given the value function that you solve, you update the policy function, and then iterate. And typically, this will give you a faster solution, so you get to the optimal point faster, but it's more prone to coding errors, at least to me. Okay. Okay. Yes.
In your experience, what's the difference between value function and policy function iteration?
So my problem with Atwish, there's no difference almost. I remember when I shouldn't like give estimates because I just don't remember. I tried it in one of my marketing classes, but you guys can try it in the example I give you, and then try the policy function iteration and see whether there's a difference. And so there shouldn't be if my codes are correct. All right. But for more complex problems, policy function iteration is faster. And the intuition I have is very simple. Because with policy function iteration, you just need to choose policies, and typically the number of policies are pretty limited. Let's say in discrete choice problem, you either choose to disclose or not disclose. Right? With value function iteration, it's kind of, it's the value function is the discounted future utility. And you can make a large, like the utility, the number that you get, the utility units can be large, but in practice, it may have very little impact on decisions, right? If you think about a logit model, and it has exponential terms, right? So the utility can be really large, but then it has no effect on decisions. So you have a better sense of this in the afternoon in the codes that I give you guys. You can see that with finite sample, the empirical value function using the CCP framework that we'll just talk about in a few minutes, using that framework, the empirical value function is not that close to the actual value function. But it has very little impact on the probability of choosing actions, just because of the logit formula. So then you don't have to be as precise with the value function as with the policy function. So that's the reason why policy function iteration gives you a faster solution. So that's just my intuition. I don't have mathematical proof. Okay. Okay. So the next one is this is a general framework about how to estimate, how to solve for value function and the policy function, using value function iteration and policy function iteration. The next one I'm going to talk about is that oftentimes with dynamic discrete choice problems, you can get away with solving for the value function iteration, so solving for value function. Instead, there is a framework called conditional choice probability framework. Then you can just apply, and it's very simple. And there's very little iteration involved. So everything that I just talked about doesn't have to be applied. So the conditional choice probability framework is basically is an alternative. And I'm going to illustrate this application using a paper that I have with Edwidge. So at this point, I'm going to switch the format of the lecture to more like a workshop-based format so that you guys can participate a little bit more. But I would say, like, in addition to this workshop format, I would encourage you guys to think about how the estimation is done. So if you were to have this problem, you try to answer this research question. So what are the practical concerns and ways that you can extend the model? Okay, and then we can always come with the theoretical assumptions that would make the model richer. Then we can also think about how we can make sure that we have enough data to identify those models that you have in mind. All right, so that's going to be something I will try out so that you guys don't fall asleep because it's getting to lunchtime. And then also we'll use this same framework to apply to the codes that I gave you guys in the afternoon. All right? Okay. So what is the research question? So the question we're trying to answer here is to understand dynamic incentives in auditor choice and evaluate mandatory audit rotation policy. Okay? So this mandatory auditor rotation is an important policy relevant question, but we don't have the counterfactual world in which we observe this mandatory rotation. So it's currently being rolled out in Europe, but in the US, we don't have this setting. So to think about what would happen if you do have this rotation, so what are the first order incentives that the audit firms or the client firms would face? So it's going to be structural estimation is going to be useful in addressing this question. So our approach will be we have a very simple dynamic discrete choice model, and it captures 3 state variables, auditor tenure, size, and prior year misstatement choices. So in other words, we are going to have this decision, the auditor choice and the misstatement choices to depend on these 3 state variables. Okay? As a practical matter, typically for dynamic problems, there is a curse of dimensionality problem. So you're not able to admit too many state variables. And there is another practical concern here, because we are estimating a dynamic problem. So we are imposing a lot of assumptions on the economic agents to be able to forecast what would happen in the future. A lot of cases, this is not a realistic assumption. Let's say I have 10 state variables. So if I do impose 10 state variables, that means that economic agents would have to forecast, okay, with some precision how this state variable would evolve over time. Okay, of course, that evolution can be random. So then the agent would need to be able to solve what future actions he or she would take in those future state of the world and feed it back to the current decision. So that's really difficult to do, right? So you need to think about, whether economy in the tomorrow is good or bad. If it's good, then what decision I'll make. But there's also other, like your capital structure decision may be different depending on the future state. It just becomes a really, really complex problem to solve. So that's another practical reason why or not we don't have too many state variables. Okay, but our approach again is simple. Okay, auditor tenure, size, and prior year misstatement choices. Okay, the key mechanism in the model that we're interested in isolating is to assume that the clients consider the effective choosing an auditor in the current time on both the current period utility and expected future utility. Okay, so that hence the dynamic framework. And this is relevant in the policy experiment we're interested in because, so when there is mandatory rotation, it cuts the horizon of the clients. So the client knows that he or she is going to have to switch the auditor, let's say in the next 2 years, and that's presumably is going to change the behavior, right? Compared to the world in which you can stay with the audit firm forever. So that's the idea. So it needs a dynamic framework. Then the mandatory auditor rotation, okay, the second mechanism is that mandatory auditor rotation reduces the expected utility from retaining the incumbent auditor. Okay, so that the intuition for this is that if I know that I have to switch an auditor in the near future, if I get a good deal, I may switch early. So that's the idea. But if I know that I have to, I can stay with the auditor forever, then to some extent I'm more patient. I'm less likely to switch. So we would observe that the switching rate increases. We also observe the big four market share decreases. So that's because of the way that the current period utility function works. So when firms switch, what we observe empirically is that they are more likely to switch across from Big Four to non-Big Four in the data. So I'll give you why that's the case. We'll explain why that's the case in a minute. But empirically, what we observe is that conditional on switching, a client firm is more likely to switch from Big Four to non-Big Four rather than within Big Four. Okay, so that might be a little bit counterintuitive. So we're going to, like in our policy experiment, we're going to exploit like other scenarios in which you are more likely to switch within Big Four rather than like from Big Four to non-Big Four. Yes. Oh no, so it's not assumed in the model. So it's just it's the fact from the data. So we're not assuming it. Otherwise, that would be problematic. Yeah. But even like so I'll talk about that point when we see the results. Okay. Yes.
The second point about lowballing or about learning, we're going to see a model, right? We're going to write this out.
Yeah, so it will be a very stylized. So we'll see the model. So we can't really pin down the exact mechanism why this happens. You'll see like the utility function would only depend on the tenure, the audit firm size, and then primary statement, linear combination of the three. So then we wouldn't be able to answer the question why the tenure arises endogenously, whether it's because of low balling or because of entrenchment. So the mechanism will be, we can't already answer those. Okay. And we'll explain when we jump to the utility function why we're doing that. And the final mechanism is the mandatory rotation reduces tenure and hence the expected future benefits of pursuing misstatements. So that's what we find in the data, and then therefore the misstatement rates decrease. Okay, a little bit about the auditing market. So the choice set, the Big Four auditors, in terms of number of clients in our data, is about 52%. In terms of audit fees, it will be much larger. It's over 90%. Over 900 non-Big Four audit firms that controls the rest of the market. There's simplification that we make. We're going to assume that there's only differentiation between Big Four and non-Big Four. So that's a choice that a lot of prior studies also use. But of course, you can do more differentiation, but we're just interested in like the Big Four market share and non-Big Four market share and what's the switching rate. So we're just going to make this simplifying assumption here. And in terms of the practical application, we're going to assume 4 Big Fours. To allow for switching within non-Big Four without imposing identity, we are going to assume like 2 identical non-Big Fours, okay? To allow for switching within non-Big audit firms. Okay. Before I show you the model, let me just try to convince you what is the first order empirical phenomenon we try to capture here. This first one is switching rate by tenure. Here you can see that as auditor tenure gets longer, the switching rate decreases. The bottom line is when the previous auditor is a Big Four audit firm. Then the upper one, the green one, is when the previous auditor is non-Big Four. Okay, there's a spike around year 16, but that's just driven by noise in the data. So there, I think we have less than 100 observations. So the distribution of auditor tenure is very thin. It's like a power law. So it's very thin at this part, in this part. So in the end, what we choose to do is to truncate the experience, Winsorize the experience when, at this point. I think we Winsorize at 11 years or 15 years. I think it's 15 years. So that's the relation between switching rates and tenure. And our model hopefully captures this relationship. Okay. The second one is the switching rate of Big Four firms. So that means that when you, in the previous year, if you have a Big Four audit firm, then what is the switching rate? You can see that the switching rate to another Big Four is pretty low. So conditional on you having a Big Four and you switch, the probability of switching to another big four is lower than that to switch to a non-big four. Okay, so that's just a fact in the data. And you can have multiple interpretations of this fact, right? So it could be that the switching is not driven by the clients. Maybe the client is fired by the audit firm. We can't really observe it. So we can only see whether there's a switch or not. Okay, so my point is that it doesn't necessarily be driven by client's preferences. Okay, so there could be the client receive a shock, the error term, and then that drives the client to switch away. So our model wouldn't be able to answer why that occurs. We can only observe an equilibrium relation between the switching rate and tenure. Okay, and then we are going to take this relation as given to some extent when we answer the policy experiment, like we examine the policy experiment. Okay, so this is the switching rate, but the thing to keep in mind here is that the probability of switching to another big four is actually lower, and that's going to be seen from the utility function estimates. Yes?
What happens if a client has auditor number 1 and then switch to number 2 and then comes back to number 1?
Okay, so you basically, that's going to be part of the switching within big four. So it's going to be captured here. Yeah, it will be reset. Okay, the tenure will be reset. So that's how tenure is measured. Yes?
I'm missing something. Should these probabilities not add to 1? So either you're switching to a non-big four or to another big four?
I think it would. Let me see. So it's probability switch to another big four and probability switch to, so these two?
Yeah.
So this is not conditional on switching, so you can also keep your current auditor.
Oh, okay.
Okay. Yeah. Did I say conditional on switching? So I apologize if I said that. Yeah.
I thought switching rate would increase with tenure.
It's
It's not true.
not true. So it's in most so this can be explained by learning, for instance. So if you know your auditor really well, then you're less likely to switch. So that's an empirical fact.
Okay. But in your model, you kind of assume it's mandatory rotating.
Yeah.
Okay.
So in the counterfactual analysis, we would assume that they have to switch at some point. Yes.
In terms of the left-hand red, are these in firms that have had no, sorry, after all, this is particularly a question.
Yeah.
The firms on the left have been, just recently had a big four auditor and then switched out. It could be that they're rotating among, that they've had big four auditors in the past for many, many years. It's just that the most recent one they only had for a very short time period.
Mm-hmm.
Or is it that they were, I'm asking about more detail on the data, if you know this. Are they firms that, just recently switched from non-big four to big four and then had to switch back?
Okay. So I don't know exactly what's in our data. So to answer your question. But I think what happened typically is that when firms had a big four, and then they switch to non-big four, is sometimes because of, at least from the audit literature, it's because of the change in the client audit firm alignment. So maybe, like for instance, after the SOX, so there's a paper by Landsman, so they basically say that the risk preferences of the audit firm has changed, and therefore they fired a lot of clients, and these clients cannot really find a big four auditor, so they just go to non-big four. Okay, so, and then when they go to non-big four, there is a learning here, so they don't know which audit firm works the best, so then they're more likely to experiment. So that's what I suspect is going on, but I don't know off the top of my head whether it's just because they recently just had a big four. And then,
Do you know about the timing for a lot of these switches right around SOX?
I don't know. So basically take the entire history as given. So there are definitely a lot of nuances in the data that we could exploit. So that will justify more like a subsample analysis. But we don't know like exactly the hypotheses. We can definitely come up with stories to explain. But currently I just want to plot some regularities in data. So this is mainly to justify why the state variables are chosen, because obviously whether you had a big 4 in the past or not matters in terms of your switching rate and whether you switch to a big 4 or non-big 4 when you do decide. And this is when the prior audit firm is a non-big 4. You can see that the probability of, given that your prior auditor is a non-big 4, then the probability of switching to a big 4, which is in the bottom part, is also pretty low. And then the probability of switching to another big 4 is higher. The most frequent decision, which I don't plot here, is keeping the incumbent auditor. So that's the most frequent decision that a firm would choose. So switching audit firm can be really costly, so firms don't do that very often. Okay? So that's the empirical pattern. Then misstatement rates. This is separately for whether a prior year has a misstatement or not. This is only detected misstatement. It's not the potential misstatement that we don't observe in the data, so we don't model that. So this is only detected once. If you misstated in a prior year, then you're also more likely to misstate again. So this is consistent with what we would expect. So earnings management is the key, so you don't just manage for 1 year. Okay? All right, so now the period utility. So the client, when making the audit firm this choice decision, would condition his or her decision on the X, which is the incumbent auditor tenure. So X is tenure. K is the identity of the incumbent auditor. R is the prior year misstatement choice. Okay? And then the utility function depends on the state and the choice. Okay, think about how many choices we have. So we have 6 auditors, 4 big 4s, and 2 non-big 4s, right? 6 choices. We have the misstatement choice. So that's 6 times 2. We have 12 different choices. Okay, you can choose to switch to big 4 number 2, number 3, number 4, 2 non-big 4s. Okay, and then you can choose to misstate or not. So there are many choices that you can make. Okay, you can also choose to stay with the incumbent. And we assume that there's an error term that we don't observe. So they collectively represent other decision relevant factors. And then this error term will be distributed type 1 extreme value. And the reason why we are assuming it is that it will give us a really nice closed form solution. Okay, as we'll see in a minute, that we can apply the CCP framework. And this is correspond, if we don't have a dynamic problem, this will just collapse to a conditional logic problem, a multinomial logic problem. Okay? All right. Yes. No, please.
It looks, relative to what we normally think of as a theory model, looks rather like everything's driven into utility functions rather than modeling. Is that, because of limitations imposed by the data? What's the reason behind that choice?
Yeah, that's a great question.
Yeah.
So this is a pretty much empirical model. So the reason why we are doing this, we could just model it, a specific mechanism through which the audit tenure arises endogenously. We could do that. But then that will just pin it down to a specific mechanism. What we're interested in is to recover the equilibrium relation between tenure size and auditor choice. And then we're going to take that preference as given. And so we can't really answer like exactly what mechanism there is that drives this relation. We'll just take the preference as given, assuming that agents will behave similarly, will receive the same utility as they would do when they choose the big 4 audit firms prior to the rotation. The only thing that will change is the horizon. So that's what we're interested in. So in other words, we treat this utility as preferences and assume that they are the same. You can argue that maybe the preferences change. So we would do some sort of robustness checks on that or scenario analysis on that. That's what we plan to do. But currently, this is the approach that's given. So only the equilibrium relation that's recovered. So this, yes.
These dynamic investment choices.
Yeah.
Isn't that they look very similar? You've got a single person choice.
Yeah.
In the dynamic single person utility flow, states are observable, like the capital stock.
Yeah.
So how do we connect the two approaches, given that they don't look the same the way you present them?
Okay, so you're saying that, so here, the state transition is in a way, I think it's just similar though, right? So the tenure, if you keep the auditor, the tenure will increase by 1. And if in the capital stock, if there is, you make an investment, the capital stock would increase. But there's no depreciation, so that's what we don't have.
So you're saying we can't convert it back to what the, say, depreciation rate by observing the coefficient on that analysis?
Yeah.
Right.
Yeah, so I think that's not way to put it. Or it could be captured by the coefficient before the tenure to some extent. So it's a net effect. So here, let me just clarify. So this is, I get a lot of questions on why this utility function is chosen. So here, the only thing we can recover is the equilibrium relation between the switching rate and tenure. So if you ask me why this relation appears, without modeling the mechanism, I can't really answer that question. So that's, you can view this as a downside of the research design, if you will, because that's the only thing that we can recover. And then when we move to the policy experiment, we are going to make the assumption that agent's preference or utility from choosing the audit firm and the Big Four would be the same. Okay? So if I get some benefits from choosing a Big Four now, I get the same benefit when the auditor firm rotation rule is kicked in. So under this assumption, then would my behavior change? You can see that your behavior will change a great deal, okay, even without any other simultaneous changes. And if you ask me, do we believe that the agents or the client firm's preferences will be the same? Of course, we don't believe that. But we need to start the analysis somewhere, assuming that their preferences don't change, what would happen? And then we can build more complex models to say, like, what if their preference changes? What if the audit firm's behavior changes when the mandatory rotation rule kicks in? So that's sort of how we envision our model. Okay. Yes.
So these parameters,
Yes.
they're all forms of the space states, right?
Sorry?
The parameters, delta,
Yeah.
all depending on K.
Right. Yeah, it's a fully flexible model. So in other words, the effective tenure on the utility depends on what's your existing audit firm and your existing misstatement choice, and it also depends on what you will choose. Okay, so that's a fully flexible utility function. So in the end, we have a ton of parameters to estimate, so we need to be clever in terms of how we apply the estimation. So the stage transition is as follows. If you choose the same audit firm, then the tenure increases by 1. If you switch auditor, then next year you will have your tenure will be reset. You'll become 1 again. And then if you switch, then of course your next period auditor will be some other audit firms, whichever audit firm that you choose. And then your misstatement choice in the next period will be just your prior misstatement choice of the next year will be your current misstatement choice. Then the firm chooses a sequence of discrete choices to maximize the expected future utility. So that's the same problem we've seen with a little bit more messier notations here. Okay, so how do we solve it? Again, we can write the so-called choice specific value function here. So the value function here does not depend on the shock. Right now, that the choice specific value function, this is just how I define it. It depends on the per period utility, okay, net of error terms again, plus the expected future utility. Okay, where J is the period T potential auditor choice, and S is the potential misstatement choice. Again, conditional on the state X is tenure, K is the incumbent auditor choice, so the incumbent audit firms, and the R is the prior year misstatement choice. Okay, the ex-ante value function can be written in this form. Okay, you can Google the property of type 1 extreme value distribution. Then you can see that it's equal to the natural logarithm of everything. Okay, all the choice-specific utility function exponentiated, okay, and summed together. So this is choice of mid-state or not, S is equal to 0, 1, and J is the auditor choice from the first 4 big 4 audit firms, and then the 2 non-big 4 audit firms, okay? This guy happened to be the denominator of a choice probability. If you look at the logic model, then you see that in the denominator of the logic model is the sum of all the choice-specific utility terms. Okay, so we basically exploit this by rearranging the term. So we can divide, okay, we can basically pull out one of the choices from this guy inside the natural logarithm. And once we pull it out, okay, you get this form. Okay, so from this form, you can see that the choice-specific value function is equal to the per period utility function plus another choice-specific value function minus the probability of making choices. Okay, so this will give you a starting point to estimate the choice-specific value functions. Why? Because this will be a just system of linear equations. The choice probabilities can be non-parametrically estimated from the data, right? In the data, you observe what choices that firms make, right? So which auditors they choose, which misstatement choices they make. So you can estimate the P, the choice-specific probabilities, non-parametrically. And then what's left will be just this system of linear equations. Okay, so this really simplifies the analysis. So in the simple example that I gave you, I post online, so you can see it's a very simple framework. So there's no misstatement choice. You only have auditor replacement problem. You just can derive it by yourself. It will take a very simple form, and the estimation will be extremely straightforward. But this is a somewhat more complex application of the notes I gave you guys. So I really encourage all of you to try it out in the afternoon, and you can ask me any questions you may have. But here, the basic idea is just to, again, write out this explicitly. So they are maximizing the expected future utility, right? And you take the expectation of this, so that gives you the ex-ante value before you even make any choices. And then you can show mathematically, so given the type 1 extreme value, the property of the type 1 extreme value distribution, you can get this closed form. So that's the nice thing about a logic formula. Okay? And then you can estimate it using this. All right. Yes?
I think it's a dumb question. So I can kind of see why maybe it's the case you said earlier that the lower beta is, the quicker it estimates it.
Yeah.
Right, because you put less worry on getting the future utility right and
Yeah.
therefore the CCP right. Can your model also then handle, if I assume a lower beta, just naturally, can I handle more states, the larger state space too, computationally?
That's a good question. I have never tried. But I think the main problem is if you assume more state is about estimating the state transition. So if your state variables are not random, so like tenure, so it just changes from one year to the next, that will be fine.
Is it going like just for not mixed use stuff?
Yeah.
Give myself an excuse. Is the fact that you can estimate faster coming with a lower beta coming from the fact that if you're iterating to make sure that this gets as close as possible to the right answer, like you don't care as much about future utility?
That's right. Yeah. Yeah. But you wouldn't be able to. I'm not sure, but I don't think it would give you, more room to add more state variables, just because practically it's just harder to estimate a state transition.
Right.
Yeah. Okay. So estimation assumptions. So will be again the period utility is as follows. It depends on the state, the current X, so auditor tenure, and it depends on the incumbent audit firm identity. It also depends on prior year misstatement choices. We're going to assume again homogeneity within Big Four and within non-Big Four. We're going to normalize parameters related to switching to a non-Big Four and choosing no misstatement to 0. And why do we need a normalization? Because with discrete choice models, you always need to normalize one choice, right? Because if you increase the utility of one choice, all the choice together, right, then the relative, as long as the relative utility stays the same, then the choice probability will be the same. So that means you have to normalize one of the choices. Okay. So this is just a random choice that we choose. So all the utility now will be expressed relative to switching to a non-big 4 and choosing no misstatement. Okay? The nice thing about this, we can just apply the Stata package, C-logit, to alternative, so that's the stand for conditional logic. Then we need to change the data to alternative specific format. If you have applied the C-logit formula, then in Stata, so you would know this. So you just need to change the data format. And specifically what I mean by that is you need to state the data in such a way that, for each given observation, you have 12, in my case, different potential choices. Those correspond to the 6 Alder-Firm choices and then the 2 misstatement choices. Okay, so for each observation, you need to expand to allow for the 6 different potential choices. That's 12 different potential choices. So that's what I mean by changing the data format. And then specify the choice-specific utilities, so that Vj of S, okay, and given the state variables. And this will be the formula that you see here, okay? You can mathematically solve for the system of linear equations. And hopefully everyone has Mathematica, so you can just use Mathematica to solve it. And it's just, there are too many equations, you may make errors. It's just better off that you code it up in Mathematica, okay? All right. And then derive the coefficients estimates from the regression outputs. Okay, so that's the final step. All right. Before I give you the results, so let's just talk about some other practical issues. The first one you may worry about is standard errors, right? So why would we worry about standard errors? Because when we apply, we estimate, we basically substitute the empirical probabilities into the formula here. So the P is not the actual P, it's the P hat, right? So then we might be worried about standard errors, but there's a paper that shows that in the case of dynamic discrete choice problems, standard errors is not an issue. So here, in other words, even though that you are substituting the P with P hat, the empirical probabilities in the data, you don't need to correct for the standard errors. And the intuition of this result is that this empirical probability is under the assumption of an optimal choice. So if you derive it, you will see that it doesn't really contribute to the information matrix, okay, if you apply the maximum likelihood method. So that's sort of the intuition. So it's an optimal choice, therefore the first derivative is 0, and then it doesn't really contribute to the information matrix in the end. So we don't need to worry about standard errors, but that's only asymptotically. In finite sample, we may still worry about it. So what I would do, now the codes that I give you guys, what I do in the paper with Edwidge. So what we do is that we get the coefficient, we plug it in, we iterate it a few times, so that we get the theoretical correct probabilities. Okay. So in other words, we plug in the P hat, and then we get the coefficient estimates. Okay. And once we have the coefficient estimates, then we can solve for the P hat again. Right? So we have the coefficient estimates, we can compute the choice probabilities, and then we use that choice probability that we compute from the new coefficient estimates, plug it in here, and re-estimate a model until we achieve convergence. So that will be, I think it's to some extent a better way. So there's a paper that shows that you only need to iterate 2 or 3 times just to get to the efficient point. But we did more than that, so we estimate until it converges, but you don't have to do that. if you have a more complex problem. Okay, so that's the estimation. So let's just, yes?
Yeah, more general question. When you run your regression to estimate your parameters of the model, you obviously assume that the behavior is optimal. Just like when you plug in the p-hat, you use it to do the rest, and you assume that the behavior is optimal and so everything fits.
Yeah.
So it seems to me that you shouldn't have, so I understand your convergence procedure to have something consistent with the model, but you shouldn't have results that are so different. Otherwise, the implicit assumption that behavior is optimal wouldn't be very justified.
Yeah, so we wouldn't have something that's very different. You're absolutely right. And the reason why we might, if we go back to, so this is really a good practical question. So I did not realize that until I actually work on this project. So if we come here, so when the tenure reaches this point, like when tenure is really long, so we only have a few observations here. So the empirical probability here will be estimated extremely imprecisely. So that results in the deviation. And this problem is also seen in the simulated data code that I give you guys. You can see that the empirical probability and the actual probability would be different, even with a large number of simulated draws. So that's the reason why we need to iterate. And that's another reason why we need to be careful in making inferences in the state of the world in which the number of observations is very small, because we don't have enough information there. So let's say if my research question is about what happens to these firms with 20 years of tenure, I only have a few of those firms, and therefore the amount of inferences I can make about those firms will be limited. So that's a great question. All right. Okay, so here is the parameter estimates that we get. You can see that we have a ton of parameters to estimate. So the model is actually pretty flexible. That allows us to recover the equilibrium relation between the Alder-Firm choice and the Measurement choice given the state variables. Okay, so it's a very flexible model. So therefore, our model fits the data really well. So this goes back to the question of whether good model fit is a good sign or not. So I'm also on the side of Jeremy, which I don't think a good model fit is necessarily a good criteria. So in our case, our model fits the data really, really well. But it's just because we are just estimating an equilibrium relation between the Alder-Firm choice, the Measurement choice, and tenure, and Alder-Firm size, and all that, state variables. So our model fit, the goodness of model fit is almost by assumption, because we are using maximum likelihood. Okay. There are a lot of mechanisms that we don't specify that we could potentially do. For instance, you could imagine that there is a bargaining process between the Alder-Firm and the client, and then the bargaining process may change when the mandatory rotation rule kicks in. So this might be something that you'll be interested in extending it, right? So let's think about what would happen if we just incorporate this. You need to estimate, at least in the current regime with no rotation, so what are the preferences of the Alder firms and the preference of the client firms? At least you have to be able to separate the two. But with the current data we have, we only have to observe the choices, right? So whether they choose an Alder or not. So then with this data, there's no way that you can separate the two, right? So you need more variable about Alder firms. Let's say, what is, for instance, like what is their litigation concern? So if they condone like more earnings management by the client firms, would they get sued? So that would be the Alder firm's preference, and that would may in turn allow you to identify something more interesting, like more detailed mechanisms. So there's always going to be a trade-off between whether your model captures the data well, or how many mechanisms you want to build into the model. So here we're just making one of the choices. So we're definitely not saying that this is the best choice, but this allows us to at least recover a relation between tenure and the Alder firm choice. So that's how we do it. In terms of the model fit, I should have just plotted these variables, these probabilities in the same graph. I think we'll do that in the future. But this is just probability of switching given tenure, pulling everything together. So this blue greenish line is the full sample. So you can see that the switching probably goes down over time, over tenure. Right? You also see that the switching rate is lower for when the incumbent audit firm is, I think this is switching, incumbent audit firm is a Big Four audit firm, and then it's higher when the incumbent audit firm is not Big Four. This is the misstatement rate. So this is the graph that matches the misstatement rate that we saw empirically. So below is when there's no prior year misstatement. Above is there is a prior year misstatement. Let's just go back a few graphs. So this is what you see in the data, and that's what comes out of the model. Okay, the two match pretty well. Okay. All right. So now we are going to do something else. We have the model. Okay. We estimate the per period utility, and now we are going to do some quantifications. So what do we do? The first one is, because the whole idea is to quantify how important the dynamic choice is. So we want to quantify the ratio between the expected future utility and the current period utility. Of course, the whole quantification depends on the assumption on the discount rate. Okay? And discount rate that we choose in estimating these models will be 0.92, which correspond to the average equity premium that correspond to our sample period. So this will be a choice, okay? So that the researchers choose, and it's consistent with the choice that other people have used. So this is basically the ratio between the two, and we find that the ratio increases with tenure. So as tenure increases, the expected future utility will be more important for you, okay? So you derive more utility from keeping the incumbent auditor when the tenure is longer. And the ratio is also larger when the incumbent is a Big Four, okay? And this has implications for what would happen when there is mandatory audit firm rotation. So let's think about it. So if the expected future utility increases with tenure, and now you're capping the tenure, okay? So that means that you're going to lose a big chunk of utility. So therefore, you're more likely to switch. Okay, so that's the effect of the first finding. The ratio increases with tenure. That would make you more likely to switch because keeping the incumbent auditor is less beneficial. The second one is the ratio is larger than when the incumbent audit firm is a Big Four. So that means that the Big Four market share would decrease, right? Because when there's no mandatory rotation, the Big Four audit firm has a larger expected future utility. When you cap the auditor tenure, the firm has to switch. They're going to lose part of that expected future utility. And this expected future utility is larger for Big Four audit firms, and therefore firms are more likely to switch away from Big Four audit firms, and that's why the Big Four market share is going to decrease. Okay, and I already said this. So the final point I want to point out is that if a client engaged in a prior year misstatement, he also extracts a larger rent by misstating again, regardless of the auditor type. So that's also something we observe in the data, but I just want to point it out again. Okay. Now is the more interesting piece. So we estimate the whole thing and go through all this pain just to arrive at this point, right? So the mandatory rotation, audit firm rotation. So the analysis currently relies on a couple of critical assumptions that we don't think necessarily map into the reality. So because again, we don't know what would happen because it's a counterfactual world. So we're just entertaining different assumptions here. So this will be one of the set of assumptions that we make. So the first one is the period utility stay the same. In other words, we treat the period utility as preferences, right? So you may get certain utility from choosing a Big Four audit firm, and that utility stays the same. So you like the Big Four the same way as before and after the mandatory audit firm rotation. So you can always imagine the state of world in which this is true, right? So big 4, it has higher quality presumably, so you would like a higher quality the same way before and after the mandatory audit firm rotation. Okay, so that's going to be the assumption we're making. Of course, you can imagine the state of the world in which this might fail. So then we can make other assumptions about how the per period utility would change in that state of the world. For example, you may think that a greater competition among audit firms may somehow change the audit quality of Big 4 auditors versus non-Big 4. So then that would change the client's preferences for Big 4 versus non-Big 4. Right? So in that state of the world, then this utility staying the same wouldn't hold. So then we can imagine or create another counterfactual world in which this other side would also fit. So in other words, the preferences may change. But currently, the result that you see will be assuming that the preferences stay the same. And then we adjust the value function. Why do we do it? Because with mandatory audit firm rotation, the maximum amount of tenure changes, right? So it's capped, so therefore the agent's behavior will be different. So this is the main margin that drives our result. And this is the mechanism that we're interested in. And to some extent, this drives our choice of model because we want to say that we recover the period utility, but then the only thing that we change is the expected future utility given this period utility. We're not necessarily interested in a specific mechanism that explains the behavior. So we just want to take the equilibrium relation as given at this point. And then finally, we account for client entering and exiting. So this is just empirical concern because in the data, you see that some firms actually, especially non-Big 4 clients, actually drop out of the sample. So this is the survivorship bias, if you will. As we look at the counterfactual world, we need to account for this because it would affect the Big 4 market share because if non-Big 4 firms, actually they are losing clients over time, and then they're also gaining new clients from Big 4 audit firms, that in equilibrium you may see different Big 4 market share, especially when we move to the counterfactual world, right? And the assumption we're making is that about 12% of non-Big 4 clients drop out of the sample, and about 6% of Big 4 clients also drop out of the sample. And these clients will be replaced with new clients, and these new clients will choose Big 4 with 77% of the time. So where do we get the numbers? We just look at our data, and then we figure it out. We also look at other papers that look at the exit and entry, and then we get the numbers. Okay? And what do we do exactly? We vary the mandatory rotation between 2 years and 10 years. And in the codes I give you guys, I don't have the mandatory audit firm rotation, but this is something you can also examine because it's an auditor replacement problem. Okay? There's no different horizontal differentiation across the auditors, but there is a replacement problem. You can see what happens if you cap the tenure, and then you can estimate what would happen if there is mandatory audit firm rotation. Okay? And what are the steps for this counterfactual analysis? And I think to some extent it's generalizable to other policy experiments as well. So you just want to start with the joint distribution of the state variables. You need to start with somewhere. So what we do is that we use the last year of our data. So that's the tenure and outer size and prior year misstatement choice in 2015. So there are 132 possible combinations of state variables. Okay, so that's, if you think about the amount of data you have, okay, you are cutting the data into 132 different pieces. Okay, so you already get some sense of the curse of dimensionality problem that we're facing here, right? So when you estimate a dynamic model, even with the simple model that we have here, you are cutting the data into 132 pieces. Imagine that you have another state variable that's imposed on top of it, then you will cut the data into even more pieces, right? It's 132 times the other state variable that you choose. And if you choose a continuous state variable and you assume that the grid point is 10, then you are going to cut the data by 1,320 different pieces. And one of these cells will have a value of 0. So there's no data in certain cell. and that's going to create a problem because, you know, are you going to assume that the probability of a transition into that state is 0? Obviously, that wouldn't be realistic. You need to make some other assumptions. Eventually, you need to make some parametric assumptions. Yeah. Yes.
Maybe it doesn't matter here because you don't have heterogeneity across big four auditors and you're not explicitly modeling switching costs.
Yeah.
But how would you implement a mandatory rotation in like a real world setting where you eliminate the possibility that I stayed with Deloitte for 8 years and then I went to PwC for 1 year and then just went right back? It's almost like a guest auditor for a year. How would I do that?
So in this model, that's allowed. It's just there's no different.
You don't have heterogeneity, so
Yeah, I don't have a heterogeneity
but
here.
if you added it, I think it would matter. Right? Because you just almost take it as like if you had really something in the future you really cared about, let me just switch now and then get back to the auditor that.
Yeah, it would just. Okay, so go back. What would happen? So that can definitely be accommodated. So you just have more variables parameter to estimate.
Okay.
Yeah, this is already a ton, so it's already imposing a lot of constraints on the data. So that's just practical reason.
Okay. I was just curious for
Yeah, no. And also another thing is that the switching within the big fours, they are just kind of similar. So unless you allow for like within industry differentiation, so then you have even more parameters to do something. Yeah. Yeah, that's right. Okay, so then joint distribution, you start with the state, so 132 possible confidence in the state variables, and then the Markov transition matrix. Okay, so then it's 132 times 132. So that's another cut on the data. So, and multiply the Markov transition matrix with an entry and exit matrix. So that's the entry and exit we just assumed in the third bullet point. And then we can iterate the model and compute the long-run state. Okay. In the end, what you see is the output, and this is what we report in the paper. So the rows are rotation years. The first column is the big four market share. The second column is the misstatement rate, and third column is the switching rate. The bottom one is the no rotation case. You can see that the big four controls a ton of market share, 65%. Remember, in the data, it's around like 52%-ish, right? So that's the no rotation case. And the misstatement rate is about 5%, which is close to what we observed in the data. And switching rate is about 12%. But once you impose the rotation, things change. So the switching rate, first of all, increases dramatically. If you just impose 2-year rotation rule, they're going to switch about 43% of the time. But with no rotation, it's only 12% of the time. And as we saw in the graph, when the client switch auditors, they're more likely to switch to a non-big four. Okay, so that's again an empirical fact. So we just take that fact as given, and then we see that the big four market share decreases, which is consistent with the increase in the switching rate. So what Edwidge and I were currently planning to do is to assume what happens if you constrain the choice set of the clients. If they do switch, suppose they only switch within big four or within non-big four, what would happen? So that's something we plan to work on. And then the misstatement rate decreases from 5% to about 2% if you impose mandatory rotation. But we wouldn't call this like a really large effect because you normally wouldn't impose a 2-year rotation rule. It will be like somewhere around 10 or even longer. If it's 10, then it's just 4.2%. It's almost the same as 5%. Okay, when you consider the standard errors and all that. Okay. All right. So question.
So have you tried? So you say like
Yeah.
one of the important assumptions that the parameters that you estimate stay the same between
Right.
the two worlds, right?
Yeah.
Have you tried simulating and re-estimating? So like, let's say you run your experiment, you simulate the data, and then you estimate the parameters to check that they didn't change.
Oh yeah. So basically, you're saying that we generate simulated data with the parameter estimates, and then we re-estimate it.
Yeah, Yeah.
Oh, so we definitely have done something like this. So that's the very first thing that I did
So
when I
my-
checked
my-
the codes.
My,
Yeah.
my concern is that within your flow function, your utility function, you have the tenure time.
Mhm.
So the Bellman equation is dynamic because it takes into account
Right.
this particular time effect,
Right.
which is separated between the utility function of the flow right now and
Right.
the expectation you have later.
Yeah.
So, for example, my intuition would be that the value that you have of an auditor is linked to the expected amount of time that you will keep staying with this auditor.
Yeah.
And in the Bellman equation, I would say, well, that's in the expectation, so the second part.
Right.
But because you have the tenure time in your utility function, I'm afraid that you might have this value in both your utility and within the Bellman equation. Maybe we can talk about that.
Yeah. So I can see like it would be in both because it's part of the utility function and the expected future.
But if it's in both, then it's difficult to assume that the parameter stays constant because in the first world, you have expectation in the data that you will stay with the auditor for, I don't know, 10 years. But in your simulated world, your expectation is much shorter.
Right.
And
So
then if you believe that this value that is coming from the expectation of how long you're going to stay with the auditor.
Oh, I see what you're
is
saying.
into the utility function, you can't assume that the parameter stays constant.
okay. So yeah. So that would be like another thing that we can change, another scenario that we can analyze. So my earlier example of constraining within the Big Four, so it basically it's another practical concern, right? So if you have to switch, then it's better off that you switch to someone who you're familiar with. So that's one issue. Another issue is sort of the reason why we see, well, I guess the reason why we see high switching rates from Big Four to non-Big Four is that Big Four audit firm wouldn't take these clients because they are the bad ones. But when we impose the mandatory rotation rule, then we can reasonably assume that on average everyone is a good guy, so they're just forced to rotate. So then the preferences of the auditor wouldn't stay the same, right? So that's another, it's like similar to what you're concerned about. So it's basically, but your concern is more like coming from the tenure part, right? Yeah. So then, but okay, so our model wouldn't be able to accommodate that unless we build into the specific mechanism that you have in mind, right? Yes. But there are other mechanisms that we can also entertain, right?
So it seems from your results, longer tenure, lower audit cost.
So right, yeah.
But longer tenure may hurt auditors' independence, but it can also hurt auditors' learning about the client.
Right.
So it's like independence versus competency. So where is the force of competency
Yeah.
in your model?
Yeah. So like this is another excellent question. So this will be the sort of the type of question you would get when you work on a structural model. So there will be all these other forces that your model is not able to capture. So those will be the force that we just choose to omit. So we're not saying those forces are not important. It's just there are so many mechanisms that explain the relation. So they're commingled together. We're not able to separate it. So in other words, we would have to assume is that the effect of those forces on your period utility will stay the same. It would not depend on the mandatory audit firm rotation. So, or if you think that's not realistic, then we can create a scenario in which this is true and then see, like, simulate what would happen. But then we wouldn't be able to incorporate it into the model and then estimate it, right? So just briefly to answer your question, that it's definitely there. It could be possible, but then our data is not able to recover these two mechanisms separately. And that even if we can, then we also need to think about what would happen if there is mandatory audit firm rotation, right?
I think some of the mandatory regime, they take 5 years. Or
Right.
If from this result, it seems like 2 years is the best, so why there?
Okay, so that's also a good point. Here, I just want to say that we need to interpret these results carefully. So this is only coming from the margin that your expectation of the future changes. Everything else stays the same. So, but we can't really assume everything else stays the same, right? So this is only one of the marginal effect of mandatory audit firm rotation. So this is not saying that once you impose the rotation rule, this would definitely happen. So this is only one of the margins. Okay, but if, from a policy perspective, then you can think about, if just changing the expectation has a dismargin effect, then should we be careful with implementing this rule because that itself has a large effect. But then something else may change which may amplify or reduce the effect we see. So like your example will be one of them. But it's really difficult to some extent because the first thing that jump into your head is that the world that you're simulating does not exist. So therefore, do we learn much from this simulation? So my answer is that yes, we still do learn a ton because just by changing this one margin, then you can change the store behavior. So I think that's interesting to know. So that would be my imperfect answer. Yes. Yeah.
I find sort of holding the preferences fixed.
Yeah.
This rule very hard to buy into. So, I'm interested in descriptive statistics of, sort of what you're
Yeah.
able to get out of the first part. Counterfactual analysis seems really tough for me. Is there a way to say that, the first part already tells you a lot, that's useful, and maybe this points the way toward, the next step, how you would build a model that would be able to tell you more about counterfactual analysis?
Yeah, so I'll definitely say yes. So that's definitely one of our research objective. But I would say even if you build, let's say we build into more detailed mechanisms, then we still need to make some assumptions about how those mechanisms would change before and after the mandatory rotation rule. And here I would just say our objective is mainly that we hold everything else constant. Let's look at this marginal effect. So we're not going to tell policymakers that this would happen.
I just worry, you say those are small changes, those are huge changes.
Right, in 2 years?
I think you're going to have,
Yeah.
people tell you that these just aren't believable counterfactuals.
Well, so people, I would say this again is subjective. So the 2 years rotation rule is not realistic in the first place, right? So you have to rotate every 2 years. Of course, that's going to change your decision drastically. So whether this is 2.4 or 17.5 is realistic or not depends on whether you think the 2 years rotation rule is realistic or not. Practically, for instance, Europe, they imposed a rotation rule of 10 years, right? 10 years. So then what we get in terms of Big Four market share will be much closer to our current regime, right? But again, so I wouldn't say this will be definitely what would happen. So we are trying to be very careful here. So think about, let's say a randomized experiment. You shock one thing, and then you see the marginal effect. But then you're not changing the whole equilibrium here. So here is we shock one thing, and then we shock the horizon, and this is what you see. We hold everything else constant. But then there could be other mechanism that would lead to the change that could either amplify or reduce the impact. That's something we can't really say.
The class exercise was opening yesterday, so
Yeah.
can we speculate a little bit about the theory that would make these utility coefficients change as a function of rotation? So can we create real time? So what do you have in mind that would be an additional step for modeling?
Learning, lowballing, lowballing.
So what is a lowballing exactly? So the model of lowballing that we have in mind? What would we?
Would be that there's some cost to switching and that.
That's there, right? There is a cost.
And then you end up with, value to staying in the relationship that, you recapture the auditor recaptures the lowball fee across time.
So prices themselves are choice variable by the auditor, is that what?
Yeah, so I can definitely see that, and then the lowballing could change because the horizon of the firm changes. So there are two things here. So the first one is how to identify that from the data. And the second one, that more generally, all the counterfactual analysis that the structural model performs has to assume that some preferences are the same before and after. So ultimately, within the lowballing, we have to assume that the per period utility of the audit firm stays the same, but then it's just the horizon of the auditor changes. But you can also say that the
the per period utility of the audit firm may also change because the competition changes. So like there's and then you have to bring in like the competition among the audit firms. So there is definitely trade-off there. So at some point, so the beauty of the counterfactual analysis, I would say, is that it gives you a tool to assume that some underlying preferences are the same. So we always need to assume that to be able to conduct counterfactual analysis. If we can't really assume that, then there's, it just can't be done. Yes.
I mean, that would be per period utility for learning would change. Mandatory rotation is going to exist, right? But modeling that would be hard. Not only that, in my world, like even giving you a marginal effect before and after policy change becomes possible.
Yeah. Yeah, agreed. And also, like, you think about per period utility for learning, if the quality of the signal sort of stays the same, then before after it will be the same. But if the mandatory rotation changes the quality of the signal, then we have to think about, what exactly, how exactly that happens. I fully agree. Yeah. So like, you can sort of see, like, even in your mind, there will be some practical considerations that would lead you to conclude whether a model is realistic or not, and what is the effect they were capturing, whether that's realistic or not. So this is definitely some challenges that you are going to face. But if you don't do this step, right? Like if you just say that, okay, so here is what describes the data. So in the data, it seems that the role of expected future utility is really important. So that drives a ton of choices. And then from this, you can already infer that given that it's so important, if you cut it, then you're going to see some effect on auditor switching, right? So then if you just stop there, that's fine as well. So we just take it to another step, of course, that's going to impose additional assumptions. So that's sort of what we do. I think that's what we want to talk about. The next lecture will be more about more general structures. And then we're going to apply, I'll just be very quick with this, more general structure, and then we're going to apply the codes in the data and then see, you guys can see for yourself, like, what is the practical consideration that you need to face and the trade-off you need to make when you estimate structural model. All right? Yeah. Have a good lunch.
So almost towards the end, right? So no, I know that, there's another thing that you've learned, okay, so I'll let Jeremy's coming back. But anyway, there's a ton of things that you have learned, and probably you have a number of research ideas that you want to try out. Just practically, my personal experience when I was a PhD student was that I was often too critical about my own research idea. So I just need to think about whether the predictions make sense. And I was even going so far as to build a model to justify my predictions. So it was a supply chain model, and about voluntary disclosure and all that. So I thought, the economic force was definitely there, because it was going to be my curriculum paper, so the second year paper with the Chicago guys. So the second year paper, and then I tested it in the data. It just does not happen in the data at all. So I don't even get any variation in the dependent variable. It's always 1, there's no 0. So I'll just say that when you have something, just don't think too much. If you feel like the marginal improvement to your idea is kind of limited, just go ahead and test it out in the data if you're working on empirical research, right? So a lot of the economic force is out there. So the models are correct. Like these, I don't think I made mathematical errors. It's just a matter of whether it's strong enough, strong enough force in the data that will allow you to identify and recover the economic primitives, right? So that would be my advice. And especially for structural work, if you don't do it, then you sort of always think outside of the box. You feel like you should add this, add that. Once you do it, then you will see that you don't want to add those things because you would make the model intractable, or the data wouldn't allow you to identify the parameters you're interested in. So that's typically the second constraints that are binding. You just don't have the data to identify those work. Let's say, to give you a good example, I think it's a good example, right? So let's say the management wants to accumulate reputation when disclosing information. So that sounds intuitive. But then if you want to build a model, then you want to tell readers like reputation for what, right? So then, and also another concern is reputation is not observable. Then you have to come up with a structure to estimate it. Let's say, you know, reputation is for being forthcoming. So for some exogenous reasons, the market just rewards the honest guy. Okay? But then, you know, the extent to which the market rewards the honest guy may depend on the firm characteristics. And then you have to make assumptions about those firm characteristics, and some people are bound not to like those assumptions, right? So they say they depends on X and Y and Z, but then some people will come up with W, right? So you just, at some point, you just need to say, okay, here is my structure, and here is how I'm going to estimate it, right? So there's an unlimited number of things that you can endogenize. So you just need to be careful with those. Okay. All right. So in the afternoon session, so I talk about an application of the CCP framework, and you also have your own judgment about, you know, the issues with the paper. So this is definitely a first step application. So we're not able to incorporate all those details and all those mechanisms. It's always going to, so our paper can only take the relationship as given and forward stimulate. And then we've discussed, you know, there's something that's unsatisfying about this approach, but then we view it as sort of like a marginal effect. So this is the first response that you would see. Of course, other responses would be built into this response. And then I say you see an increased switching rate. So that's driven by the forward-looking incentives. But then the increase in the switching rate could result in other changes that we don't model. So that definitely can happen, but it's the first step. So if you use impose the mandatory rotation, this is the first response that you will see, but then there will be subsequent responses that we don't model. All right? So now I want to give you a somewhat more general framework. And the reason why I'm doing this is that to give you something to rely on. So I don't expect you to sort of understand all the techniques I'm going to introduce because they just make everything more complex. And when you write a paper, you're not going to explain them in great details because, well, most of these readers, you just impose significant amount of cost on the readers, and they're going to get confused. And as you will see in a minute, so the structure can get really complex. But this is to give you a general framework to think about. Let's say a dynamic decision choice model has 3 elements. A decision maker chooses among k plus 1 alternatives. Okay, so this is already constraining our model in a single agent framework. Okay, so just one agent making decisions. So already here, people are going to challenge you to say that a lot of practical applications will have economic interactions among agents. So this is sort of an Earth is the center of the universe comment. Right? So think about the regression you're running. Right? So a lot of people, if you look at the auditing literature, they regress the auditor firm choice on a set of firm characteristics. Right? So there, you're not making the assumption so explicit. So in that model, you're also, the firm is making the decision to choose or not to choose an auditor, right? So there's also no economic interactions. But my point here is that you're making this assumption really explicit for readers to see and criticize, right? But here, the problem we're dealing with is a single decision maker making decisions. Choosing among k plus 1 alternatives, and in our setting will be audit firms. State vector is x as its observables, and then epsilon is not. So those are the error terms. You can assume they are, Gumbel distribution, type 1 extreme value distribution, or they can be multivariate normal distribution. Okay. Then the transition density of the observable vector is t mu t plus 1 conditional mu t. And here people can also criticize, it would not only depend on mu t, but also mu t minus 1 minus 2. Okay? So we're going to say, okay, we think as a first order approximation, the transition of the state depends on the previous state. Okay, that may be off empirically, but then we have to make the trade-off. If you code it up, you will see immediately that even allow for randomness in the state transition impose a ton of constraints on the data. All right, 3 assumptions are typically made. Additive utility, separability. So utility from choosing action depends on the utility and the error term. They're separable. Okay, sometimes you make a multiplicative separability assumption depending on our research question. But here we're going to assume this additive separable. And the next one is conditional independence. So that's really important, to get really well-behaved value function, and it's really important for identification purpose. Is given x and at, so xt is the state variable observed by the econometrician. At is the action that the agents are choosing. And the realization of the epsilon, the error term, does not influence xt plus 1. So basically, your unobservables would not affect the future observed states. And once you make this assumption, people say, oh, that's crazy. You can, of course, think about a scenario in which the error terms can be correlated with the future states, right? But then that goes back to the OLS regression. If you assume that the error term is correlated with your regressors, you have a correlated omitted variable problem. You can't really estimate anything, right? So all the OLS regressions, we are implicitly assuming the conditional independence as well, right? So the conditional on the regressors, so the error term is independent of the conditional mean of the error term conditional on the regressors is 0, right? So that's what we assume in the regressions. This is just basically mirror image of what we have to assume in the dynamic distributed choice model. Okay? Yes?
I'm not sure. I mean, I understand what you're saying,
Uh-huh.
but let's assume that I have a model with stochasticity after the action, like stochasticity,
Right.
right? The thing that you are telling us that we shouldn't have. If I estimate it using, let's say, maximum likelihood or
Right.
GMM, do you think that would be problematic?
So it's not, the correlation is not identified, right? So if you assume, like in OLS regression, right, if you assume the regressor is correlated with the error term, then you can't really recover the true relationship.
in a regression form. So
Here it's the same. You can show that it's the same. You can also not recover the relationship. Like, not even think about the decision choice. Like, just think about how you can identify this density is not trivial, right? So the error term affects the current state. The current state affects the future state. But then you can't really recover this correlation. It's just like writing a regression. You can't really assume that the y and x and epsilon have a linear relation, but then x and epsilon are correlated. So if you know the correlation parameter, then everything is fine. But if you don't know it having estimated, then there's just no way you can do it. Yeah. Because you can always change the correlation and parameter, and then just change another parameter that rationalizes the data. So that's the sort of the intuition. I know it's not as precise, but you can show it mathematically. All right, the third one is IID assumption. So that can be relaxed. So the epsilon JT can be correlated across alternatives. It just make it really hard to estimate. But then you would have like something like a nested logic if you have heard of from your econometrics class. So that would allow some correlation within your choice set, the epsilons. It can also be correlated across time, just the epsilon itself, and that will make it really hard to estimate, but it's feasible. There's a recent paper, 2018-ish, paper published in JAR that used this approach. So they assume that error terms are correlated over time, but at the same time, because they assume that, they have to impose a really simple structure. Otherwise, they can't really identify it from the data. Just rule of thumb, mean is very easy to identify. Variance is harder. Covariance is also hard because it's second moment. And if you want to go higher moments like kurtosis, then you are just. But I have never tried, but you're not going to go very far. Yes.
So sorry, very quickly again on the point before.
Yeah.
That means that you can never estimate models with multiple agents.
What do you mean?
And so let's say we play a game, right?
Yeah.
In most games, I would make an action, and you would make an action, and that would be the next state.
Yeah.
Before I make a new action.
Yeah.
So my action can result in different states. So
Yeah.
you are in a situation where you have stochastic states after the action choice.
Yeah.
And that means that violates this
Oh, I see.
given xtat, there is no stochasticity after that, and you know your state xt plus 1.
So my point here is that here the epsilon t is unobservable. But in your example, like if you observe the action that's chosen by those agents, and if they interact, you can still estimate it. But
Oh,
if
you mean that you wouldn't consider it as a stochastic problem on the part of the agent?
so they can still be stochastic, and then they can still you can still assume that they choose something based on the. Oh, I see what you're saying. So you're basically saying the action itself is stochastic.
No, but like
from
I'm sorry, maybe we
from
can talk about it.
econometrics perspective, it's stochastic.
Yeah, from the perspective of one agent, it's stochastic.
So that's fine. That's allowed.
Okay.
So here it's purely like it's out of the control by the agent.
Yeah.
So here is that's the epsilon is separable, and then you just don't know anything about it.
Okay.
So then if you don't know anything about it, you can't really assume that there is a relation of this epsilon with other variables. So maybe that's the best way to explain this. So if you're truly agnostic about something, then you can't really simultaneously assume that it has a known relationship with some other variables. Okay. So again, the same solution. So I'm just breaking out the purity utility into two pieces, and then the expected future utility. And here I have two densities, right? The observables, which is x. So there's the density of x prime, so that's the future x, given the current state and the choice, the action j. And then there's also the g prime, so that's the unobserved shock that also could change over time. Okay, here the g epsilon prime can depend on epsilon. So the unobservable themselves can have persistence. They can't interact with the observables. All right, and then also define the ex-ante-value function, which is the v conditional on x and epsilon integrate out the shock term here, so the epsilon j. So that's ex-ante-value function. Sometimes either of the two can be handy depending on the problem. So I just gave you both. And then you can use the ex-ante-value function omega x to solve for the choice-specific value functions. And I'm doing this because with a lot of dynamic district choice problem, it's much easier to work with ex-ante-value function. So basically, do not assume that you observe the shock terms. And the intuition for this, the intuition for why having ex-ante-value function is easier to solve is not because of mathematics. It's just because computer memory. Right, so you can see here, we have, let's say, 6 choices. In our paper, we have 12 choices. Then we have to store for each observation in the data set 12 different shock terms. And then let's say you have 40,000 observations. That's a lot of things to store in the computer memory. That's going to slow you down dramatically. Because a lot of times, computational speed is not just about how efficient your computer is. It's about how much memory that you have. The more memories you have, the better. Here, working with ex-ante-value function reduces the dimensionality of your choice problems. So that's why it's preferred. All right. So then, again, ex-ante-value function, the omega x is choice-specific value function integrated out the unobserved error terms. Okay. Now the senior faculty is not here, I guess. So if you have any questions, just feel free to ask. All right. You're not going to just at some point you have to overcome that barrier. As you become a professor, you have to ask questions. As junior faculty, you can't really just sit there and just don't ask any questions. You have to ask something. Right. So if you have any questions, just feel free to ask. And then I'm happy also to start from scratch and just describe the choice problem. Or if you want to ask individually afterward, that's fine as well. But it's better just to ask questions as you come up with them. I'm completely flexible. All right. Okay. So now some numerical issues. From this moment on, so this will be just the tools that you can use. So if you think about, okay, so there is a problem I'm going to solve, and then you don't know how to solve it, you can remember the lecture notes, you can just refer to this, and then you can Google, there are a ton of other lecture notes that explain the details. So I'll just get something for you to start with. So how do we store the value of x when the state variable is continuous? So we're talking about discretizing the state space, but then people would say that, you can't really say performance is only taking 3 values, high, medium, and low. Performance is continuous. What would happen if you allow for continuous state variables?
But what will happen is that you're going to have a ton of breakpoints and you can't resolve anything. You can't obviously, can't really answer that way. You could, but that wouldn't be accurate. So there are ways to allow for continuous state variables. And then how do we evaluate omega x? Specifically, what I mean is how do we compute the integral? Okay, so we have a huge, our value function is already numerically solved. Then we need to integrate it. And sometimes, even worse, we need to take the derivative. Right? So we don't even have a closed form. How can we just integrate it and take derivatives? And sometimes people ask for second order derivatives even harder. So what do we do then? So that's the problem we're facing. The first one to allow for continuous state variable is just to say that, okay, so I'm going to discretize the state space, and I'm going to connect the dots, right? Connect each dots, and that will be my value function. There are different ways of connecting dots, but at first let me talk about discretization, and then you have a better appreciation why I don't have many state variables. Why when people ask me like, why don't you just incorporate this other mechanism, this other state variable that could also be relevant, and people have shown that it's relevant. Why? We're not doing those. Okay. So the first one is I want to point out is that we can choose, a finite number of points. Let's say we have k state variables. X belongs to this k-dimensional vector. Then for each dimension k, we will discretize it to n points. So that's xk1 to xkn. So in the end, we have k to the power n combinations of grid points. So for transition density, we can do the same thing, right? So now it becomes a Markov transition density. So we have k to the power n number of state points, and then it would transit to the same number of state points in the future, and you need to just specify the transition probability. Because all the x's are observable, this probability can be estimated non-parametrically using sample frequencies, right? So the problem, as you can see from the slides, is already that before you even estimate the model, just estimating the state transition probability, you can already get a curse of dimensionality problem. So let's say that we have 3 state variables. So that's what number of state variables we have in that table at which 3 explanatory variables. So empirical study has far more than this number of state variables. That's how many they have fixed effects, right? So 3 state variables discretize into 10 grid points. So that doesn't sound many. But then that will be 1,000 different combinations of state variables. And you are estimating the Markov transition matrix for 1,000 times 1,000 different buckets. So obviously for each bucket, you're not going to get very precise estimate. So you have to do something, right? Typically, you just need to reduce the number of dimensions. That's the first thing. You always need to do that's the most effective one. Second one is to impose parametric assumptions, smooth out. Like you probably have heard of the kernel density estimates. You have to do some smoothing. So this is not so much. This is not data mining. Okay, so this is necessary because otherwise you're going to get one of those cells with 0 probability, and that's definitely a problem, right? So that can't be the case in real data, right? So you have to do some smoothing here, and there are a non-parametric approach. You can do kernel density, you can do other approaches. Okay. And then another way to connect the state vector, so compute the value function, is by the spline method. So, or the interpolation. The interpolation assumes that it's linear connections. So let's say you have only one state variable, okay? Performance low, medium, high. And then you're just connecting the value function when the performance is low with the value function, the value when the performance is medium and high, and then just linear connections. So that's the interpolation. But if you want to take derivatives, because the linear connection has kinks, so that's property is not very good, so you can do spline. So that's basically polynomial connections. So that's one of Jeremy's papers that he's working on. So use the spline method if I understand correctly. But here the grid points are still chosen arbitrarily, right? So you just divide it into 10 buckets or 3 buckets, depending on your preference. So there are smart ways to choose the nodes, and that's
called orthogonal polynomials. So this is one of the approaches I will explain just briefly. So the application is kind of complex. If you are interested in using it, then I'll give you my code. So I have a short assignment that I did not post online, but I have a code that allow you to do this. So it's a pretty cool method. It just approximates functions really accurately. So instead of discretizing the state space and then approximating omega x, so we can approximate the omega x, which is the x anti-value function, globally using linear combinations of easy to evaluate functions. So those are the t's. So the n is the total number or degree of the basis functions, and p denotes the ith basis function. So the t of I you can think about is a special form of polynomial with degree I. So that's the idea. Okay. The Chebyshev approximation is one of the often used orthogonal polynomial method. So the way that the Chebyshev approximation works, okay, is basically computing the n degree, the t of t subscript n x is this cosine formula. It may not look like a polynomial, but I assure you that it is a polynomial because you can iteratively compute the t of n as a function of t of n minus 1 and t of n minus 2 in this way. But you need to set the t of 0 to 1, t of 1 to x. So this is just pre-specified, right? So there's nothing that, so this step can be computed outside of any loop. So that gives the computational efficiency. So you don't have to do the value function iteration, right? So with this, you can pre-compute the t's without letting them enter in the loop. So that saves you a ton of time. If you try to apply this method, you can see that try to avoid as much as possible anything that goes into the loop. Because as you loop stuff, there's more computational time. As I said, if you think about 20,000 iterations, it takes 1 second, you need to just, it takes about 3 months to produce the outputs. So you can't really afford it. So this can be pre-computed. What I mean by that, again, in case it's not clear, let's say that x is performance, right? So performance, and then let's say we already have a set of grid points, okay? And then what you're going to do is that x will be plugged into here, and then you apply this formula in the end, okay? But of course, the x would currently at this time, the x is not going to be like for performance. I'll explain how you extend to more realistic variables. Now x is just some arbitrary, let's say, state vector that we are interested in. Okay? So we're now really talking about multi-dimensional problems right now. Okay, how do we do this? So here is how you do it. The first step, we're going to choose the degree of polynomials. So I call it n, the number of interpolation points. So that's n. And n has to be larger than n. Why? Because in the end, we're going to run a so-called Chebyshev regression. And then n degree of polynomials will really mean n plus 1 regressors. So you need more than the number of variables, okay, number of regressors to recover the coefficient. So that's why the n has to be larger than or equal to n plus 1. So that's pretty nice. Typically, a good, well-behaved value function can be approximated using like 2 or 3 degrees, right? 5 degrees at most. Then you don't have to choose many grid points, right? If you have 2 degrees, you can just choose 2 or 3, maybe 3 grid points, right? 3 grid points, or even larger with 5. So m is based on your preference, okay? So that will save a lot of computer memory when you try to store the values. The second step is to compute the interpolation node. How do we do this? We call it new I, apply the cosine formula as follows. And then the third step is to adjust the nodes to interval a and b. So what are those a and b's? Those will be actual state variable that you observe in the data. Okay? Suppose performance in your data takes the value from like -2 to +2. Then A will be -2, B will be +2. Practically, you just want to ensure that it covers the minimum value of your state variable and then the maximum value of the state variable. this wouldn't be any loss of generality because you can't really extrapolate outside of the observation that you're observing the data anyways. So it's okay to just truncate the grid points to the minimum and maximum value of the state variable. So here B again will be the maximum performance in my example, and then A will be the minimum performance in the data. Okay? This mu, the second step, can always be computed without any data. So it's just a cosine formula. Okay? And now, in the fourth step, you evaluate the function at each nodes. Okay, Ci. So that's the t when mu is 1, so t0, t1, tn. When mu is 2, then t0, t1, tn, and until mu is mu m. So basically the idea here is that for each interpolation node, that you are going to compute the n-degree polynomials. So you can view this as a regression format, right? So each of the n-degree polynomials will be your regressor, and then each of the n points will be the data points. Okay, then you can recover, run the regression, and then get a coefficient vector x prime x, inverse x prime y. And then this will be the, it will give you the value function. Okay? Just to make it clear here, remember in the value, this is not a substitute for value function iteration. You are still going to do that, it's just fewer grid points. So for each iteration, remember we were just arbitrarily guessing a starting point of value function iteration, right? So we start with like all the value function takes 0, so arbitrary point. And then this y will be known, so it will be all zeros. And the x will be computed from step 1, 2, 3. And then you run a regression, recover the coefficient before the polynomials, and then this will be a theta vector of coefficients. Okay? Remember that in the end, the outcome variable y is equal to theta, the sum of thetas times the regressors. So this is what this Chebyshev regression is doing. Okay? And then in the end, the function that you get at that will be the sum of the regression coefficient times this guy. So this is just mapping x, the state variable, back to the unit interval. Because here, this x takes the value from 0 to 1. Okay, so it's because of the t of x takes the value from 0 to 1 because of the cosine formula. Okay, so that's the basic idea, and you can show that when the degree of a Chebyshev approximation goes to infinity, then it converges, okay, to the true function, and uniformly. And then I would say like Chebyshev approximation does not work well in the following case when f is not differentiable. Okay, because this makes sense because you're using a polynomial by construction is differentiable, but if the true value function is not differentiable, then you can't reuse it. One example in accounting would be that you have earnings management around the threshold, then you have a kink, then that's not differentiable. Then you're not supposed to use this. It also does not work well when f has a lot of curvature. So in this case, it's not like, it's not like it does not approximate well, so you're just better off using discretization, normal discretization, because you also need a lot of grid points to approximate f has a lot of curvature. And another thing that if you work with macro problems, oftentimes you solve for first order conditions. If you have a high degree polynomial, that may not be a good idea because you may have multiple solutions. In fact, there's just one, right? So that could happen because you have a higher degree polynomial, then you have a lot of wiggly shape, right? And then that may give you multiple solutions. So in the end, at the end of the day, so you just need to be careful with the method. Even if you use Chebyshev approximation to increase the speed, you also want to check whether you produce something that's consistent with value function iteration. Just simple things. Okay. This is again just to give you a tool to apply, and you don't have to understand all the details right now. So again, this is just only one step of the value function iteration. So we're just choosing the grid points smartly, and then given
the value function that we get from the previous iteration, so that's the y, then we can update the coefficients. Okay, so the theta, and then you're, instead of iterating over y, we are iterating over theta. So we just keep repeatedly solving for theta until it converges. And that typically is pretty fast.
So just
Yeah.
trying to make sure that I understand. So we still need to iterate.
Yeah.
It's like instead of before we are guessing a b for the value function,
Right,
now we are
exactly.
guessing an f.
Right.
And
And
then,
theta, yeah. So compute
and then
theta.
we compute theta, and then
Right.
we can recalculate a f,
Yeah. So v or f.
b or f.
Yeah,
and then
the
we-
same thing.
Okay.
Yeah. So all these methods, they're not substituting for value function iteration precisely. It's just another way. Like policy function iteration is the same case. So you guess a policy function, but in the end, you still need to compute a value function. Right? It's just an extra step. It may sound like it's an extra step, but that extra step is worth their while because it's going to save the overall computation time. Dramatically. I'm not like I wouldn't be surprised like 10 times as fast. So it's really good. Another thing is just you can use C++. That would basically increase the speed by at least 20 times. But yeah.
C++ wouldn't solve the memory problem.
Sorry?
C++ wouldn't solve the memory problem.
Oh, it wouldn't.
It would
No,
solve the memory
nothing
problem.
substitutes for the. So if you don't have a memory problem, you have a memory problem, then it just is done. Yeah, but C++, like in compared to R, then C++ is more primitive, so that's why it's faster. So that's what I mean. Yeah, you can solve the memory problem. So just. Okay. So I'll skip the multiple state variable case because it's the same. With the multiple state variables, it's very, very prone to coding errors because it involves transformation of a lot of, collection of different state variables, and then make sure that the order is correct. Especially if you're working with matrix language like MATLAB, then there might be coding errors that you make. You just want to make sure you're careful. So I'll skip this. Finally, it's just I'm going to talk about integration. So if we are computing the expected value of fx with the density px, so this will be integral. So what we're going to do is to withdraw from x from this density, right? Withdraw values from here, and then compute the average. So that will give us the integral and the expected value. There are two things. The first one is that sometimes the p of x cannot be directly drawn. If you have that problem, then I would advise that you change it so that it can be directly drawn from, because let's say you can assume that x is normally distributed, then we all know how to draw from a normal distribution, right? So this is built in. But sometimes if you want to examine some like a Bayesian updating problem, so like you have an underlying hidden Markov chain, but then the Markov process is not normal, so you can't really apply a common filter, then the problem gets messier. There are tools to deal with it, like Metropolis Hastings algorithm that can be used to deal with this problem. But I would say like start with something that can be easily done first before you apply a more complex method. As Yufei said, more complexity doesn't mean that it's better. So people can say it's realistic, but still it doesn't mean that it's better. All right, so let's now assume that the density of x, p of x, is known, and then we can draw from in the data. So then we just draw, let's say, 1,000 points, and then take the average. That will be the expectation. It's not very straightforward, but that also slows you down. Okay? Because sometimes we're interested in evaluating the integration of the value function, which requires an iteration, right? And then you're also evaluating the at each possible realization of the state, you're also evaluating the average of the value function. That can be time consuming. So there are other ways called quadrature that you can apply to compute the expectation or the integral. So if your expectation or the integral that you're interested in take this form, so this should be familiar, so it's like a standard normal distribution at this form, right? If you take this form, then the quadrature approach, the
quadrature approach can be applied. And it will be just equal to a sum of different weights, omega wi times fxi. So these xi nodes and then weights, okay, they can be pre-computed. So even outside the loop. So that means you can just apply the formula, then you get pretty precise estimate of the integral. Right? So typically it wouldn't be like more than 5 points for one-dimensional integration problem. It's very, very precise. Okay? And then you can apply this. Okay, so this is just a general ways of dealing with numerical solutions. So remember, we think about the value function iteration problem. So here we already assume that we know the parameters that enter the utility function. So there's no estimation yet, right? So we know the utility function, the per period utility, the parameters that govern the utility function, and then we try to solve for the value function. And when we solve for a value function, we have a problem with continuous state variables. So these methods would allow you to approximate the value function relatively more precisely. Okay, so that's the idea. And then this is also another tool that you can use to compute integrals in the end. So you always want to try something kind of simple before you go to something more complex. So the next one, I will just so I discussed with Jeremy briefly. I think it makes sense for you guys to go to the website, and then there's a simple model that we'd like to estimate. But let me just briefly explain what a model is, and then how you can go ahead and estimate it. If you are using like MATLAB, that'll be fine. So you can just code it up in MATLAB. It should take about half an hour or so to code up, at least to simulate the data, and do some value function iteration that we have talked about. So the code that I posted online is pretty much self-contained. You can see that it already runs some diagnostic analysis. So sometimes I use the true value, sometimes I use the empirical data value. So just to see that whether I can get the same estimates or not. So there are plenty of robustness, but you can run more robustness. And you can, for instance, check the shape of the likelihood function and all that. Okay, so briefly, this is a simple, dynamic model of algebra choice. Let me make this larger, download it. Okay. Is better? An algebra switching problem. So this is first a state transition. So this model is extremely simple, right? There's no differentiation across auditors. The only decision the agent is making is whether to change to replace the auditor or not. So you can think about this as just a typical Rust engine replacement model. Okay, it's just imposing the auditor interpretation, so that make it more accounting, but it's just an engine replacement model. So if you keep the incumbent auditor, the state tenure will increase by 1. If you don't keep it and switch, then the next year the number of tenure will become, the years of tenure will become 1 as well. Okay. Sorry. If you keep, then it increases by 1. If you replace, then it becomes 1. Right? Next year. The length of the auditor relation can be unbounded. So in the data, long auditing experience is very thinly populated. So we're going to assume that after the state reaches year 15, then it stops growing. Okay, so it's just bounded. Because you just don't have enough information to see what's going on when the tenure is long, and the transition, the probability of switching sort of converges to a constant. So you're not going to get much variation after year 15. You can also see that from the data, given the parameter estimates. The client is only concerned whether to replace the current auditor or not. The per period utility is this. So gamma 0 plus gamma times xt. So I could say that's gamma 1, but I think I forget the subscript. And then plus beta times the expected future utility. So this capital V is the extensive value function that I just talked about. It's already integrating away the shocks, right? And here, the value function, I'm just omitting the shock term. Right, so the shock is going to be type 1 extreme value distributed. Okay. So the epsilon 1t and epsilon 0t, I'm omitting it from the value function here. So you can just add it back if you want it to be consistent with the utility function. Okay. So here is how you derive the model. So given that the error term follows type 1 extreme value distribution, we obtain that V of 1. So that's when the firm chooses to retain the auditor. So V of 1 is equal to gamma, so the property utility gamma 1 times xt plus gamma 0 plus beta times V of 0 xt plus 1 and minus beta log of p0. So 0 means choosing to replace the auditor. Okay, and against it variable is xt plus 1. So the p is the probability of choosing to replace the auditor. So you can approximate this p0 in the data. Okay, so you observe in the data, given that the state of 10 raised xt plus 1, what is the probability of the client switching auditors? Okay, so that would be the number we're going to plug in. Okay, and then you can rewrite this. One thing that's, so then you can also do this for V0 xt, that will be equal to V0 of 1, so that's 1 year of tenure, because after you switch, we assume that the tenure will be reset to 1, so that's from the state transition, right? And then minus beta of natural logarithm of P0, 1, so that's given that the state is 1 year, then what is the probability of replacement, okay? So the P0 of 1 can also be estimated from the data. And you can see from the second line is the V0 of x. So when the state variable takes the value of x, it's the same as V0 of 1, right? So it's just, it does not depend on x. So basically the second line, the value of replace that you get from replacing the audit firm, okay, with another one, does not depend on the state. Okay, does not depend on x. But that means that you can just substitute the second line to the first line and then compute the difference in the utility, which will give you equation 4. And you can see that this has a really nice format, right? It's nice because it is the same property utility plus an adjustment term. This adjustment term can be computed non-parametrically from the data, right? So it's basically the log difference of the probability of switching the auditor, okay, replacing the auditor given the tenure is 1, minus the natural logarithm of the probability of switching the auditor when the tenure is xt plus 1. Okay, and then you can form, given that the error term is type 1 extreme value, so you have the logit formula, so then it's basically the likelihood function is e to the power delta v xt divided by 1 plus the e to the power delta vxt. And then this can be estimated pretty easily. You can use data, or you can use R, you can use MATLAB, so it will be pretty straightforward. In data, you just use the logic formula. The only difference is that you have to constrain the intercept, right? Because you have this term here, okay, beta times the natural logarithm of the choice probabilities. So in the article that I gave you guys, so hopefully you can download it right now. So we basically assume again xt can take 15 values from 1 to 15. We'll simulate 3,000 firms so that we have a large sample, each with 15 periods. Okay. And then we are going to assume these parameter values. And in that we try to recover this parameter. And you can see that I have various techniques. The good thing I think is a good practice is that I simulate data first and making sure that I can get the true parameter values based on the simulated data, and then I apply it to the actual data. So you may think that just after you've done the simulation, then you use actual data, there will be no-brainers or no problem. That's definitely not true. So there may be other properties of the real data that your model does not capture well, and there will be like an iterative process of adjusting, making adjustments, tweak your codes, so that you can deal with this practical problem. And typically it comes from like some dimension of data is just, it's not like normally distributed, it has like curvatures and some area has low density and that could cause identification problem just in practice. It just has, you have to use your experience.
All right, so with the next, time, the additional time, I think I would encourage you guys to work on this problem, such as solve. First, simulate data using value function iteration, and then try to, if you have time, to estimate the model. First, to get a sense of how the value function iteration works. Okay, you can use either R or MATLAB. So briefly, the reason why I used R in the first place was that for my dissertation, I need parallel computing. And then at that time, it's really difficult to parallelize it across different computers because you would require license for each of the computer. And at that time, it wasn't there, so it wasn't allowed because in MATLAB, you have to pay individual license for each computer. And I was trying to parallelize it across, like, I think 60 or 70 computers at the same time. And it just, as a PhD student, I couldn't afford it. But now I think I heard that there could be, if you're using cluster, there could be cluster versions of MATLAB, and also MATLAB has a parallel version itself. But that means that you can parallel within your computer using multiple cores. Stata also has that functionality right now, but it's only parallelizing within your own computer. So, but the property I was looking for is that it can be distributed across different computers at the same time, and they communicate with each other, and then they come back to me. So that's what I was hoping for, and R was kind of flexible at that point, and it's cheap, so it's free. So I just do it. Another thing is that R, at that time, it interacts really well with C and C++, and that increases speed. At some point, you just need to, go there, and if you want to increase speed. But at this point, I don't want to say that, you want to learn that because it's really time consuming. For a lot of problems, simple models, you don't need to go there. And also, the downside of R at that time was that it wasn't interacting well with nonlinear equation solvers. What I mean by that is that if you have a really nasty nonlinear problem, the MATLAB, the F solve, and an R optim is not going to give you anything that's close to the actual solution. So there are good nonlinear equation solvers that allow you to interact. Basically send it to the server, and then it will just spit out a good solution. And R wasn't able to do that, and now they have that functionality as well. So this really depends on your preference. Okay. Okay. So I'll be around, and if you have any questions, I would encourage you to try right away. Just don't waste the time because it's really important to get your hands dirty to understand what's going on. Then ask me any questions you have.
All right, thank you very much. Let's thank Frank for